Yeah, thank you. Can you hear me okay?
Yes.
Great. So thank you everyone for coming. Today, I'm very excited to tell you about our ongoing project called VODKA, which stands for Varstrometry for off-nucleus and dual sub-kiloparsec and kiloparsec AGN. I'm going to be focusing on the dual population, but our technique is also useful for searching for off-nuclear targets. I wanted to thank my collaborators and in particular, those early career researchers being highlighted in yellow here. So this talk is gonna highlight the work being enabled by mainly by two Gemini instruments, so GMOS and GNRS. And at the end, I'll also briefly mention the exciting prospect with Alopic, the speckle imager. So we wanted to thank our the amazing scientists and our support astronomers at Gemini who really help us, make the observations possible. So I understand this is a really diverse audience. So I wanted to start my talk by providing you with a bit of a background. So why do we want to study dual binary AGN or more generally supermassive black holes? As a reminder, in our own backyard, our own Milky Way galaxy is in a direct collision course with our closest neighbor Andromeda. So we are, personally relevant with this kind of cosmic interplay. And in fact, galaxy mergers have long been thought to drive strong gas inflows, producing either one or maybe two active supermassive black holes, inducing perhaps also feedback to influence the host galaxy evolution. So the dual or binary population really provides a direct tracer of the hierarchical galaxy and supermassive black hole formation. In addition, if we focus on small scales, meaning kiloparsecs or sub-kiloparsec scale, it actually provides us with another indirect tool for understanding the particle nature of dark matter. And this is because the particle nature of dark matter directly influence the dynamic of friction, which will drive the further evolution of a pair of supermassive black hole. So in some models, alternative models to the cold dark matter, instead of promoting dynamic of friction, they could actually prevent further dynamic of friction, so producing a lot of stalled supermassive black hole pairs on sub-kiloparsec scales. So in order to test this, we really need to go down to this kiloparsec, sub-kiloparsec-ish population and really understand their statistics. And last but not least, I don't perhaps need to tell you that they are also of interest to the very exciting emerging new field of gravitational wave astronomy. But you may wonder, we already have LIGO sources. Why do we want to understand or study the supermassive cousins? And this is because unlike most, if not all, LIGO stellar mass black hole binaries, most of the supermassive black hole binaries are expected to occur in gas-rich environment. And this offers a great opportunity for multi-messenger astronomy, and not just post the fact observation, but because of the longer evolution timescale, you can actually get a really early forewarning of the event happening, which means that you can get your favorite particle detector EM observatories ready long before the final coalescence actually happens. So it provides a really exciting opportunity for really comprehensive multi-messenger astrophysics. So thanks to most recently, mostly due to the event of big surveys, there has been great progress being made in the observational searches of dual and binary AGNs, which are taken as tracers of dual and binary supermassive black holes. So here on this cartoon illustration, I'm showing you some example known systems or candidates in the parameter space of binary separation as a function of redshift. And if you notice, the separation spans several orders of magnitude, going from milliparsec to subparsec to all the way to kiloparsec to 100 kiloparsec scales. And this is because we want to paint a really coherent picture of the full evolution of a pair of supermassive black holes following a galaxy merger. And you may notice that there are glaring gaps in these diagrams. And so firstly, all these objects shown at the bottom right, they are candidates. So they're basically subparsec candidates that are selected from indirect approaches, perhaps not available for direct confirmation, before gravitational wave detection. And what we would like to focus on are the population on the upper left, which really represent those that are directly confirmed systems. So if I make a similar plot by showing you, almost all the known so-called dual AGNs in the literature. So here is that plot showing on the right. You can see that although there are many dual AGNs, which are the really low luminosity counterpart of dual quasars, there are really only a handful of cases, at redshift 1 to 3-ish, around redshift 2, which is the cosmic noon, representing the peak of both quasar space density and cosmic star formation. So in order to really understand this peak supermassive black hole and star formation epoch in the universe, we really want to go to higher redshift. And so at larger scales, which means larger than 10 kiloparsec scales, there are many of these wide separation quasar pairs, but we really don't know if they are already in gravitational interaction with each other yet. So they may or may not be merging as of yet. So bottom line is that there is a glaring gap at high redshift and small separation, which we would like to fill with the VODKA project. And finally, this last plot just zoom in on the cosmic noon, showing you the really handful of candidates of dual quasars, which really represent the really highly accreting merging systems that may more likely to be directly associated with mergers. And I'm gonna return back to this figure later, but in this talk, I'm gonna be highlighting this new work, which represent the first confirmed case of a kiloparsec scale dual quasar at cosmic noon with confirmed galaxy merger. Okay, so but before telling you the details, I just wanted to say a few words about the many methods that are available to detect these systems across a whole different scales, and we draw a lot of inspiration from the stellar binary and exoplanet community. And in particular, there is the astrometry technique, which proves not to be so useful for exoplanet, but it turns out is very useful for us. I won't go through the details, but just to give you a context of the techniques that are available. And in particular, this new technique, which we called VASTrometry, which stands for variability-induced astrometry jitter. So it goes like very similar to viewing a railroad crossing sign from the distance. So notice that if you have two quasars on kiloparsec scales, so the quasars themselves are not moving, but because of the variability, perhaps due to thermal instabilities in their accretion disk, it produces this apparent shift in their unresolved light center, which we can use actually as a detection signal. Using this technique, we use Gaia astrometry, which really offers you a almost full sky survey of bright quasars. Here I'm showing you some examples of ground-based limited images of some of the VASTrometry selected kiloparsec scale dual quasar candidates. Now, in order to really test whether they are due to two or multiple sources, so really need high resolution follow-up. And we obtained dual band Hubble images. And indeed, in more than half of the sample, you find two or even multiple sources verifying that indeed this variability-induced astrometry jitter technique is working. And using the information, we can by and large reject some obvious stellar interlopers, for instance. But this is not the end of the story. And this is because in a lot of these candidates, so there's a long-standing debate about the nature of these dual quasar candidates, because you can have instead just lens images of a single quasar by a foreground galaxy, for instance. So what really is crucial is deep, high resolution near infrared imaging. And here I'm showing you an example of the first case of a confirmed dual quasar separated by about 4 kiloparsecs at cosmic noon, in which you can actually detect both tidal tails indicative of direct gravitational interaction, as well as extended host galaxies. And this is really conclusive evidence in favor of the merger hypothesis and ruling out the lensing scenario. On the bottom, we also have CAG-AO imaging, which is better in terms of the resolving power, but HST infrared imaging is better for its more stable PSF and the fainter, the deeper the surface brightness limit that it allows us to get. So that these two are really complementary to each other. And finally, to put this discovery into context again, so in contrast, all of the handful of dual quasar candidates below 10 kiloparsecs, they are either the so-called near identical quasars, which are most likely still lensed quasars instead of merging quasar pairs, or there are also cases where you see some noticeable differences in their spectral features, but they're still controversial as perhaps projected quasar pairs at large separations that are not actually merged yet. So none of these previous candidates actually has this confirmed merger signature. Okay, so finally going on to the the really highlight of this system is with Gemini spectroscopy, both in the optical and infrared, we are able to measure really key physical quantities for both the host galaxy and the supermassive black hole, and it's a very massive system, almost equal mass merger, hosted by a very, very massive galaxy merger cosmic noon. And we also have Hubble's DIS spectrum, but Gemini is really better in terms of the signal to noise that it offers, whereas Hubble obviously is better for really conclusively resolving the closed double cores. So again, these two are really complementary. And moving along, so this is almost my final slide. We also have multi-wavelength confirmation, and both in the X-rays and in the radio to study their accretion properties. And we also have in future James Webb and ALMA observations approved to understand the more detailed host galaxy star and gas contents and kinematics in future. So stay tuned for more results. So this is my summary slide. I wanted to leave you with something to look forward to. So in summary, so Gemini spectroscopy is very, very useful for spatially resolved follow-up for the larger sample of our VODKA candidates. And this is, only possible because of the really high efficiency and fast turnaround, and for us to be able to build up a large enough sample to understand the statistics in order to compare with theoretical models. And finally, I wanted to also mention that so this here is an example of a dual quasar candidates in our sample, which has a separation of 0.5 arcsecond. So it's not actually pushing the limit, but it's very faint. It's a target of only R of 19 magnitude. So it's the faintest ever image targets for a low peak. So and it's very exciting prospect for perhaps observing more of these interesting candidates to really find either dual or lens quasars. So I will stop here and take questions.
Okay, thank you, Xin. So we have just time for just maybe one or two short questions. Is there any question from Slack?
No, there's no question. I have a question.
Sure.
So I'm wondering about this obscuration properties of dual agents. So it seems like they do both show broad lines in their spectra. So do you think, but I thought that they are kind of obscured because they're merging. So do you have any idea about these obscuration properties for these dual agents?
Yeah, wonderful question. Thank you. So indeed, in mergers, and in particular gas-rich mergers at high redshift, you would expect a lot of obscuration, perhaps, not just near the nuclear region, but also in the host galaxy of the merger. But in our case, because of the sample selection, we are strongly biased against the obscure population, because we require them to be unobscured as a starting point, so that we can have the variability in their continuum emission, which means that they are unobscured AGN by definition. So this is indeed one of the limitations of the technique. So in order to get to the really intrinsic population of both obscured and unobscured population, you would need to correct for that unobscured AGN population fraction.
Okay, thank you.
Okay, thank you. I think we need to move on. So thanks the speaker one more time.